Yeah, okay. You showed a very high resolution simulation of a hot wind passing over a cooler gas, and it was disrupted. That was very high spatial resolution. And then in the bigger box, you had a resolution of 5 parsecs, and you did some resolution study, and you said it depended on the resolution. So do you care to speculate on what happens when you get 100 times more running time or whatever?
Yeah, so actually one of the reasons that I hesitated in this talk to like put numbers on, you know, the velocity of gas at a particular density at 8 kiloparsecs is because I'm not sure how much I trust those dense blobs of gas that are out there, even in my simulation, because, you know, it's very high resolution, but I demonstrated, I thought pretty convincingly to myself, that if you had much higher resolution and you could actually resolve the hydrodynamics of those blobs when they were closest to the disk, that even many more of them should be disrupted. The other piece of that that's interesting, I think, is that, you know, if you are mass loading the outflow and you have density perturbations and you have even higher resolution than we have, it's not clear to me exactly how the thermal instability will operate, but it's possible that you could then recondense cold blobs out of the hot phase as opposed to the sort of monolithic cooling that we saw if you were in sort of an intermediate case, right, with the mass loading. So, yeah, I mean, my sort of short answer is that I think even more of that stuff, the high density stuff, is going to get disrupted and added into the hot phase. But I do think, you know, because of the way that the clusters interact, you can get pretty big blobs of dense gas lofted into the outflow, and those should survive for long times and distances. Yeah.
Going back to the question that you asked in your talk, how you have cold gas at such large distances, is it the shredded pieces that have survived?
Could you use the mic, please?
I just asked, going back to Norm's question that he asked, in the how do you have such cold gases at the large heights? So is it the shredded, I mean, residues of the shredded pieces of these clouds that you have there?
Yeah, so in our simulations we see both, and I think that's actually what's really interesting about them, is that we see cool gas that's high velocity, right, like 800 kilometers a second, and relatively low density, that cooled directly out of the hot phase because it was mass loaded, and then we also see even higher density clumps that are the same temperature, right? And they should be, even though we have a temperature floor, like you've got photoionization, and so that gas should be of order 10 to the 4K because we're not dealing with the even higher density stuff. So yeah, so I think that's what's interesting is that along the same sight line we're seeing gas that should be moving at low velocity, that's pretty high density, and then gas that's slightly lower density but at high velocity, and it's all at 10 to the 4K. Yeah.
What is the mass rate outflow in your models? Can you guess?
Right, so what was the rate that we put in, or what is the rate that comes out?
No, outflow.
Right, so I'm saying I injected a certain amount of mass, right? Those were the mass loading rates that I put in, right? So at the high mass loading state, I was injecting 12 solar masses per year, just directly into the hot phase. But if I measure at 5 kiloparsecs in a sphere what MDOT is through that sphere, in the highest resolution simulation it's like 50. We're getting a lot of additional mass loading. Some of that is entrainment, but some of it's not, right? Some of it is in the hot phase. In those histograms, I mean not histograms, the radial profiles that I was showing, the median density of the gas, the low density gas, is an order of magnitude higher than what you would get if it was just the gas we had injected.
So in general, the mass outflow, the higher is the more efficient compared to what you inject in the center.
Right. Yeah. So that's exactly the point, and that efficiency goes up with resolution, and we haven't converged. So, yeah.
So I had actually a question about resolution. So you said that if you increase the resolution, you get more and more features. But is there like a physical scale, however small it is, that you expect to get like a fragmentation thing, like the CST stuff that Mike McCourt and Peng have been talking about?
Yeah.
That's tiny, but if suppose we are able to reach that, will we get converged results?
Yeah, so there are a couple of physical scales that are relevant. That's one of them, the CST cool, and the other is the scale that's set by conduction, right? So the field length, so in order to truly resolve thermal instability and the hydrodynamics, you would have to resolve both of those scales. And CST cool, unfortunately, because these outflows are very high pressure, is very, very small, right? So CST cool in the CGM might be of order a few parsecs, which is like doable for resolved studies of the CGM. But CST cool in these high pressure outflows is going to be much smaller. So in theory, yes, when we get down to that scale and we have conduction, we should be able to fully resolve the problem, but we're not going to get there anytime soon.
And they're mutually exclusive. If there's conduction, CST cool will go away.
What? Right? Yeah. No. Exactly. Right. I'm saying like those.
Yeah.
I think conduction usually actually sets the scale. So
right.
if you include conduction, which wasn't in the McCourt paper, then that's what sets the minimum scale.
So in your simulations, like after the output, right, you get high velocity, almost PUE. So and cold. So do they like again condense after output, or are they like a diffuse gas which is like just diverging?
Right. So we were seeing in the high mass loading state, we were seeing just monolithic cooling, not condensing into little blobs. But in the low mass loading state, it's not clear from the simulations that I ran if all of the cool gas is directly entrained from the ISM, or if some of that could be stuff that mixed and cooled out of the hot phase. This next set of simulations, we're going to have like passive scalars. Yeah, exactly, so that we can track that. But I also think that there's a case that we didn't really simulate, which is that sort of intermediate state. And in the intermediate state, I think it's possible that some regions of the outflow would cool and others wouldn't. But I'm not sure actually in this sort of scenario that you would ever get little like blobs, like a thermal instability type cloud blob, just because the sound speed is so fast in the outflow that those perturbations get washed out very quickly, and so then you're more likely to see like large scale cooling than individual little clouds forming.
Your coal gas is 10 to the 4.
Yes, right.
So that's
Yeah.
also another floor that
Right.
will not.
Yeah, so continuing with this cold gas thing, so is it possible to place any limits on the sizes of these cold gas clouds? And what's the total mass of this outflowing cold gas?
In real life, that's it.
Yeah, so it's a question to both observers and theorists.
This is fully limited by the observation in terms of resolution. And the best resolution we have is NGC 253, M82. Unfortunately, we don't actually have that great resolution because it's in the north. But now we're at the scale of parsecs. Yeah, it's not even. Yeah, it's not. But with ALMA, with 253, we're talking about parsecs, and that's not fully using ALMA yet. And so, we're getting there. We're getting to be, getting those clumps of 10 to the 4 particle per cubic centimeter on parsec scale. But throughout, that along that filaments, we see it. It's pretty close to the base, so it's not further out, but within the interkiloparsecs.
And also, a question for simulators. I mean, have people computed the mixing timescales? Because it's hard to imagine just some cold blob just flowing along with the hot gas. So why doesn't it mix? Well, you are the simulator.
I've been arguing that it does mix, right? I've been arguing that it does mix.
It does mix.
Yeah, right. And that's what's mass loading the hot phase, is the mixing in of the
And there are specific models that address this mixing, like just quack turbulent mixing layers where you've got intermediate temperature gas. And so people have done this on a more idealized, modeling scale. These are effects that happen on smaller scales.
Yes,
but
right.
yeah, people have thought of this, and the time scales vary with your model input parameters, but they can be on order 10 to 100 million years
Okay.
in the model.
Okay, I have an observational question. What new types of observations do we need to better our understanding of galactic winds? Sylvain mentioned JWST, maybe gamma ray burst host galaxies. Wondering if anyone had any other ideas of what data sets would really help.
So I can make a comment. I think recently we have found a way of detecting galaxies very close to quasar sightlines. It is basically using the fact that SDSS fiber thickness is about 1.5 arcsecond to 1 arcsecond depending upon when you observe. So this is very interesting case because you have star-forming galaxies and the sightlines are very close to them. And we have about 200 such sources now in the redshift range between 0.4 and 0.6. So only thing we could not do now is that we will not be able to take the spectrum of the galaxy at very good signal to noise. But we are able to get the absorption lines. So we can see the offset between absorption line and these galaxies. So these are very close impact parameter cases. Like most cases it is like average impact parameter is like 5 kiloparsec or something. So this will be very interesting if you can, I think in future at least, if you look at the down the barrel wind towards the galaxy and look at these guys which are at the same scales, right? We are not necessarily at 10, 20 kiloparsec away. It will give a very interesting constraint, I suppose.
So to answer your question specifically, I think that's something people are working on, is using new integral field spectrographs that are coming online, like MUSE and KCWI, and perhaps combining with things like gravitational lens galaxies, where you can actually separate out individual star clusters and target them with IFUs and study down the rail outflows at kiloparsec or like hundreds of parsec range. That's probably the next step we can do in the next 5 to 10 years. Yeah, in principle, you can spatially resolve the outflows and try to link it to the driving sources like the star clusters themselves.
I think also on larger scale, I mean, I think MUSE is already starting to revolutionize that field where you look at high redshift system and you can really see the nebula on CGM scale, on 100 kiloparsec scale, with 1 arc minute field of view of MUSE. And KCWI will do the same. It's already starting to do the same. It's starting to revolutionize the high redshift universe where you can actually map and get an image and spectrum every position and be able to map the CGM.
I also want to mention Lyman alpha in this context. So the kind of looking at unresolved galaxies, when we've been looking for objects that are Lyman continuum emitters especially, there have been some interesting and unexplained features with respect to the Lyman alpha apparent, trying to model the Lyman alpha profile and kind of what the implied rest velocity is relative to the rest velocity that we see from other emission lines, and there is something strange going on kinematically there. So I again encourage people to, with the simulators, to look at Lyman alpha and for the observers to get more data on that, and also other emission lines kinematics.
Doing Lyman alpha radius of transfer is impossible.
I think the solution to that is to give up on Lyman alpha and go at H alpha with the near infrared IFUs. And it's already starting to happen.
I would like to turn to the point related to conductivity and mixing. Conductivity in the ISM, in the IGM, is very strongly suppressed, as I understand, by magnetic field. Therefore, it works not quite efficiently. And it can't suppress the mass outflow because it survives the cloud against evaporation, and the cloud under radiative losses compresses, and therefore it gets hard to get it outflowing, moving at all by ramp pressure, and it also survives the cloud against mixing. So the mixing time can become longer than the dynamical time. That's my point on that.
The only place where we've seen Spitzer-like conductivity is actually the solar wind. Yeah.
Yes.
And ISM, I don't know of any observation which points towards anything
Yes, but
close to
in
Spitzer.
principle, conductivity suppresses this. Somehow it probably works under realistic conditions, but it is suppressed.
I would like to come back to the question Andrew posed on the constraints or what we should do to constrain galactic winds. I think background sources have been used to that extent, but we'll be able to use that more with large surveys like LSST, foremost, large spectroscopic surveys. You will have tons of backgrounds, sidelines to do the tomography of the IGM. In that context, I think it's going to be very important to spatially map the gas. And I think the H-alpha with IFU is great, but you're not going to go very far because the emissivity drops, as a 1/r square density square, which goes as 1/r square. But with background sources, you can probe the gas to much further distances. And we've seen that already the gas is very highly collimated in winds. And I think that's a puzzle when you see these simulations of outflows that don't seem to be so collimated. So probably that magnetic field or something plays a role.
So going back to the idea about conduction and magnetic field draping, protecting these clouds, I think that there's good arguments for that sort of in the linear regime, but there recently have been a pair of papers by Bruggen and Scanepiego that did a similar set of simulations, albeit I think at significantly lower resolution than Evans. And they found even with anisotropic thermal conduction and MHD that the nonlinear hydro instabilities and cooling are able to break up these clouds, maybe again on a time scale 2 to 3 times longer than without that, but still far longer than it would take to get them up to 800 kilometers per second, for example.
Just in that context, there's this one magic result from Mike McCord where you put in a random magnetic field, get on the top and just zoom out without anything happening. You know that is?
It was Anne-Marie Madigan's stuff.
What's that?
I think that was Anne-Marie Madigan's stuff.
The one that I saw was mine.
She was on that paper too.
Oh,
She was on that paper, and it was Elliot and Ryan O'Leary.
And they didn't do anything else. It's like what, they didn't believe it.
And we have their we have their high resolution simulations, and we see something different.
So I didn't get, so what did they just put some random magnetic fields and...
Yeah, so they put in like uniform fields and the clouds broke up.
And then they draped things and it broke up. And they did one where they put in like a random, field. Like they were saying, okay, suppose there's turbulence, you get a little small scale field. And then the cloud just got blown right out and never was disrupted.
But it was relatively low resolution. Not, in fact, incompatible with what you get without magnetic fields.
Well, that point had escaped me. Okay.
It is in the sense that like if you don't put in fields, it doesn't last as long.
But not by that much.
It was that was.
I can remember they just get the cloud survives for a few times longer.
Well, no, I thought in the one run they claimed it was till the end of their simulation. Yeah. Yeah, exactly.
I don't say it was demonstrated that at this resolution with that field and that particular structure, I think the cooling was also like a sort of a hand wavy cooling.
So the size of the cloud they had was such that cooling actually is unimportant.
Right. Yeah. So point being that it was in many ways different than other studies, so therefore it's not actually that surprising based on this. But it also doesn't surprise me that when you do it at high resolution, you see it.
Well, I don't want to. Yeah.
I have a question. So the cloud surviving time, that should also depend on your reconstructions?
So You mean the spatial reconstruction?
Yes.
Yeah, so in the same sense that it depends on the resolution, it will depend on the spatial reconstruction. So we were doing those simulations with third order reconstruction, which is actually also something that most people were doing linear reconstruction. So we had high resolution and third order reconstruction, which is just continuing to push sort of at the resolution barrier. So yes, it does depend on that. And again, until we get down to the minimum scale that's set by other physical processes, you won't see convergence.
I mean, I understand it was a lot of work to write your code. Is it like impossible to imagine doing a moving mesh or an adaptive mesh?
So no, but I'm not going to because other people are those codes. No, essentially, like we were trying to write something for a different purpose, right? So it was like there are already, if you don't care about high resolution everywhere, people have done a really good job solving that problem algorithmically.
Nobody's doing simulations.
Well, actually, people are now trying to take AMR codes and force resolution in like the rest of the box, which I find amusing.
Okay, so just for the record, I'm very skeptical that you can accelerate molecular clouds with a hot outflow. And it's for reasons, in addition to the shredding problem, it's the cross-section problem. When things get very dense, it's hard to intercept momentum and energy. And so there's been simulations done looking at cloud shredding, but you stand a better chance of accelerating the volume filling phase, modulo things like Rayleigh-Taylor instabilities and such. We'll talk more tomorrow about how to generate outflows that turn molecular. But what is the future of modeling, say, acceleration of a volume filling medium with a hot wind and the instabilities that follow?
So I guess I was with you until the last sentence because
Okay.
I mean, the volume filling medium is the hot
Well,
medium, which is accelerated.
I'll put another, yeah. So in your model, you start with a disk. And where the disk is, it is volume filling, right? Where the disk initially is.
Well, actually, that's not true.
Well,
Even the Milky Way. Oh, you mean interstellar?
per disk, yes.
Yes. Yeah. The high density gas is volume filling in the disk.
Yes.
Yes.
Okay, and I guess you're simulating that at high resolution and finding what transpires. And maybe the answer is what we just watched.
Maybe. Yeah. Right. So that's what I'm saying. I think that's the part that's hard to answer right now. I mean, partly because we have a temperature floor, right? And so the molecular
Right.
gas, it's exactly what you're saying. As you push on it with the hot phase, the molecular gas just.
And we're done.
Yeah, so it just keeps condensing, right?
Yes.
It's cooling efficiently, and then that makes it get denser. It cools.
Right, yeah.
So you end up with these like bullets that are very difficult to accelerate. So actually, right, the problem only gets harder with the molecular
Right, I guess, yeah, when it becomes not volume filling, then it tends to start decoupling. So it's kind of,
Right.
yeah.
Yeah. So I think, right, if you want molecular gas at 1,000 kilometers a second, I think my impression is right now, theoretically, we have a very hard time getting that. So you would like to pull it out of hot phase, but then you need dust.
I'll be slightly more optimistic and say it's a whole lot easier to imagine it happening through condensation than pushing rocks around with your breath.
No, I agree with you. Yeah, I think most of the arguments people have against condensation have to do with the dust, but I think there might be ways around that.
Well, yeah.
Right. Yeah. And because it was hot, then the dust should have gotten destroyed, and so then it's harder to reform molecules without dust. This isn't something I've said.
Well, tomorrow we could have a completely different conversation about the curious robustness of dust grains, but maybe now's not the time.
Any last questions?
I don't know. I don't see a mic, so I try to speak up. My question to everybody, basically, when I look at the winds, galactic winds that I've seen today in observations and modeling and simulations, they somehow looked different to me than what I see in cosmological simulations or in galaxy merger simulations with central AGN feedback. And I was always wondering if anybody, I mean, these implementations you need, of course, to get the galaxy evolution right. So is anybody worried that there's a discrepancy, or that there might be a discrepancy or some differences between what we see in observations and wind modeling and what's actually in cosmological simulations?
I worry about it every day.
The cosmological simulation people are worried.
I don't lose sleep, but I do worry about it. Obviously, it's clear that there's a mismatch. I mean, the resolution is a critical aspect. It's never. I mean, from an observer point of view, I trust these theorists. They're they're excellent, world class, etc. But I don't trust the simulations. I think that qualitatively they provide good guidance to the observation, but ultimately it's the observation that's going to win the day, because that's what we observe, and then the theory will try to catch up. Like the Milka gas outflows, that came from nowhere, from the observation, and now it has to be explained. I can speak on their behalf. It's really difficult.
So what you say then, that the cosmological simulations?
I think it's worse in the case of the cosmological simulations.
I was just going to say that for what most people call cosmological simulations, big boxes, at least 20 megaparsecs, the winds are put in by hand. They're not a simulation, they're semi-analytic models.
Yeah. We're discriminating between the simulations we saw today and their issues with observations, and cosmological simulations and their issues with observations.
So they're, they just tune the models. So that didn't used to be made clear, and it's now slightly clearer if you read the papers, I'd say. But yeah, you should be aware of any cosmological simulation. The winds are put in by hand. They're not doing any of this physics whatsoever. What they're doing is kind of crazy. I mean, all the fire simulations, which are somewhat better resolution. They're not kiloparsec resolution, several parsecs in the best case. So we get some scaling relation between the mass loss rate and star formation. And then the global simulations just take our scaling relations, which are already pretty shaky, put them in there. Now, to be fair, it's not better than any others. The original estimates just used based on arguments that I had made about momentum to see which they should do pretty quickly, but why shouldn't they? But people in the cosmological, they want to do the best. So I understand they want to do the best job they can. So they make up these semi-analytic models, use the best. But we should not, like any stretch of imagination, precision calculations.
So my stupid question is it completely clear that well, somebody made that 20 times the stellar mass of galaxies, I guess at the high mass end of the galaxy mass distribution has to be somehow cycled through the galaxies and not end up at forming stars. But is it actually transparently clear that that gas really does get cycled through the galaxies?
So Mark would claim that in certainly larger galaxies it's prevented people, it never gets in the first place. But I would say in the low mass galaxies, things well below enough main mass, there's been no plausible explanation for how you prevent gas from getting into the cores. And that's what you see in high resolution simulation. You have, again, several parsec resolution. Gas gets in.
And then with various feedback functions, it gets thrown back out again, but it's the resolution that is not involved in this fragmentation is caused.
Yeah. Well, and I'm actually the person that mentioned that, and it's worth mentioning in the context of what Norm is saying, that because it's hard to keep gas from coming into the small galaxies, you need even more to be thrown out of the, right? You need mass loading factors more like 100 to get dwarf galaxies, right? Whereas larger galaxies, you use.
We never see that. You never see what? You never see loading factors of 100.
No.
Yeah.
Although, to be honest, no. Right, the measurements are especially, it has to be at high redshift also. The 100s are redshift 2 for dwarf galaxies, so we don't have that.
You have to have a
honestly
very
have that
gas-rich
many.
disk, which you don't have locally. And then you gotta, so now you gotta do these observations of redshift too, as you say. There's no, you don't have to believe this because it's a simulation. The dark galaxies.
Well, that's what's needed to create our universe.
It's something wind time scale may be also small. Like this mass loading is very large. Most will go in short time itself, like 1 burst or 2 bursts. Maybe statistically catching them will be also difficult.
No, man, regarding the cooling or overcooling problem in low-mass galaxy, Eva, you showed that the winds do depend strongly on the resolution. So for understanding cooling might depend on the resolution as well in those low-mass computers, and therefore change our picture. Absolutely. Yeah.
The galactic potentials are also pretty shallow for dwarf galaxies.
Makes it easier to throw stuff
You
out.
just sort of, don't. It's very, very easy. The preventive feedback is also very easy in them.
Yeah, so I want to make a comment about mass loading factor, and it's the mass loading factor can mean many different things depending on what scale you're measuring. When people analyze simulations like the fire simulation, they're often calculating mass loading factor by how the outflow at like 20% of your radius compares to the star formation rate. When people try to measure it observationally, they're looking like in a kiloparsec. And so you can't even compare those.
Plus the phases are different.
Well, the phases are different, but also the scales are different. And so, when Norm is saying a lot of the gas gets into the galaxy, it doesn't mean it all gets down to kiloparsec. It's broader than that. And so the mass loading factor you need to keep that from forming stars is on a different scale than the sub-kiloparsec region where people are trying to measure mass loading factors observationally. So you have to be aware that they're not always talking about the same quantity.
So I have a question for Aditi. So, you said that there is distributed injection and centrally concentrated injection. Which of these are more realistic, or do you like have some model systems where one of them is more appropriate than the other? I think it's sort of a similar question that one can ask you, but I have to go first.
So in my presentation, I compared the two with observations, right, with the line brightness from two galaxies. And I said that it is the distributed case which matches better in this respect.
So that's true for most galaxies, or are there galaxies which are which can be modeled as like a almost centrally concentrated injection of energy? I think what you need to say is that the distributed injection is more realistic way of
because that we got from the Kennigan-Schmidt law, right?
That's, to add on to that, that's from the X-rays. Most galaxies have a much shallower X-ray profile with height above the disk than you could get from a central injection model.
So you can also look at cases where you have a very strong nuclear starburst, so that most of the star formation is limited to a nuclear region, and then that can be where you can apply your central simulation.
So one very good example is our Milky Way galaxy itself, right? So the total star formation rate in our galaxy is roughly 2 to 3 throughout the disk. But if you compare the star formation rate surface density throughout the disk, it's like pretty low, lower than the threshold like obtained by many, right? And so it doesn't launch the galactic wind from the disk. So, but if you look at the galactic center, where the star formation rate is like 0.1, quite low, less, but the star formation rate density is high. So there you can have a like galactic wind kind of thing. So it's like kind of depending on again the threshold value of the star formation rate density, whether it is above it or below.
So you're saying that central injection is a good model for?
I mean, depending on galaxies, yes. So where you have what?
Yeah, we should slowly wrap up.
My impression is, I just continue what Kartik is saying. My impression is that from the point of view of X-ray distribution, this distribution explosions, they better fit the observation. But from the point of view of the data today, Rongbong, whatever showed, the absorption in the shell, definitely in the shell. The central explosion is better to fit this data. So it depends probably on the conditions. And in this case, what we observe in the Milky Way, it's somehow not consistent from this point of view, from the X-ray observation and the absorptions in the metal absorptions in the toward the Fermi bubbles.
What was not consistent? What was not consistent?
The absorptions Rongbong Bordelot today showed, they are definitely concentrated in the shells from one and from the other side. X-ray emission, what Aditi showed today, they are concentrated in the central. They are more concentrated in the center, and it is consistent more with X-ray observations in the galaxies, in the Milky Way also.
If I can add to that too, I think the timescales are relevant because the Fermi bubbles may be something that exists on timescales of a few mega years to tens of mega years, but the X-ray halos may be built up over much longer timescales, right? So it's true that what we see in the metal lines is more suggestive of a nuclear outflow. I agree, but whether that's true in a time average sense, or whether we've just caught the Milky Way when it happens to be doing that, that's clear.
Time scales are the same. It's around 10 to 20 megayears, 10 to 30 megayears.
For the X-ray halos?
Yes, for additives. Yes. Yes, yes.
But there in this case, the star function density was high throughout the test, right? And in our Milky Way galaxy, the situation is a little different than these are star function galaxies. Plus, our galaxy has already some circumgalactic medium, which adds to the kind of surface lightness. So I'm not sure that Aditi's case is exactly relatable to the point level observations.
Yeah, I think this debate can go on for a long time, so it's better to end it at this point, and you guys are free to hang out here and discuss this further. So thanks a lot, everybody.